received his PhD degrees at the University of Texas in Austin in 1969, I think he told me. Turns out we overlapped there but never saw each other. His topic is the development of high metals, hydrotreating catalysts, the use of crystallographic concepts in catalyst design. Alan.
Seems like most people haven't been using it. I guess everybody can hear me okay. This talk is going to be as much a story as it is a presentation of information, which belies a little bit the nature of industrial research. This work was started 14 years ago. My background is obtained in X-ray crystallography at the University of Texas. And I guess what I should do is put that in there.
I need to roll out of the way, probably.
But when I came to work at Unical in 1971, one of the things I wanted to do was to try to apply structural concepts to catalyst research. And the biggest problem that I could see that they wanted to solve there at that time was what they called the resid problem in those days. And at that time, what that amounted to was to develop a new catalyst that would remove the sulfur from resid, which is the heaviest part of the petroleum fraction. The catalysts in those days contained about 12% molybdenum trioxide and about 4% cobalt oxide in alumina. And it was also known that the working phase was some kind of a mixed sulfide. So one of the things that occurred to me was to search the literature and see if I could find some kind of a mixed sulfide in the crystallographic literature that would have about that ratio of cobalt to molybdenum, and see how that stacked up against what we thought we were using at that time. Well, the structure that was found was this one, COMO2S4. I should say at the outset that it got decided about 1973 or 74, I think it was, that this compound is inactive for HDS. But as maybe a qualifier, the experiment was done on the bulk compound unsupported. And I don't know but what the compound could have come apart in the reactor and not been the same thing as the author thought. Notwithstanding, I feel a little bit like I'm in the middle of a maelstrom right now because, as you gathered from the talks this morning, and as Russ said at the outset, we're involved in what appears to me to be another golden age of research in catalysts like this, and that one more time the whole thing has been thrown to the wolves in the sense that there's lots of models, no one of them seems to be entirely correct yet. I think you'll see perhaps as we go along in this talk that this compound stands one more time and maybe as much of a chance of simulating the active side as any other model right now, but I can't claim it's right either. What is going to be shown, I think, is the power of analogy, and particularly industrial research. You know, like we all do, you have a model in your mind, and you make use of the model and try to improve your system based on the ideality. And you may end up, like I think I was to a large extent, being right for the wrong reasons. Notwithstanding, you can see from this particular structure how the atoms are arranged in this projection along the B-axis. You have the molybdenum atoms, four molybdenum atoms projected in one unit cell. There are 2 unit cells shown here. The cobalt atoms are located in these symmetric positions like this, and the sulfurs that can be projected onto the alumina surface are shown like that. The actual crystallographic data indicate that there are 2 bodies of atoms like this stacked up on top of each other. And in order to imagine a monolayer, one can cut off the top half of the structure in the ideal crystallographic representation and use this projection. If you do that, there are these 4 molybdenum atoms in each unit cell, and that's going to be important in a minute as we see what can be done with that. Can we lower the projector just a little bit for just a second? My slide is too tall. Or maybe, if it's going to be too much trouble, I'll just try to explain it from the previous. Thanks very much. The idea of this slide is to show you, taking off from the previous slide, what one can do is to calculate the area under one of those unit cells like this. This is sort of a two-dimensional counterpart of a crystallographer's density calculation in a bulk structure determination. And if one does that, one gets the equivalent molybdenum trioxide on the 300 square meter surface, using the 300 square meters and the area of the unit cell, the conversion factor of angstroms to meters, 4 molybdenum atoms per unit cell that we saw, and the molecular weight of molybdenum trioxide together with Avogadro's number to get 0.42 grams of MoO3 on 300 square meters. The equivalent amount of cobalt oxide from the COMO2S4 structure is calculated analogously to be 0.11 grams. So if one takes as a basis 1 gram of alumina, the grams of catalyst that, thanks very much, the grams of catalyst that come out of 1 gram of alumina with this ideal model is this number, and which gives 27% molybdenum trioxide and 77% cobalt oxide. That was the idea here, to recruit just a little bit, was we had 12% MoO3 and 4% cobalt oxide on these catalysts in those days, and the idea was to see whether or not we could increase the loading with constructive results beyond what everybody assumed at that time was possible. And this estimate said you probably could do that. This slide is similar to the last one in terms of the results on it, but what it does is simply to show that you get a little different answer, of course, for a support that contains 200 square meters per gram rather than 300 square meters. The surface area of the finished catalyst, which are these proportioned by the metal loadings, are these numbers. And something that will be important in a little while is that an empirical formula that accounts for these numbers is this. Weight percent of MoO3 is about 0.14 times the surface area. That ended up being important for patent purposes later on. At the time we started this work, I didn't have access to a flow reactor, so we had to use an autoclave to conduct some initial resid activities. This slide shows those of you who are not familiar with some of these feeds, what a resid feed looks like that we were using in those days. The sulfur is a concentration is around 3.88%, and this gives you an idea of the boiling range, about 480 degrees Fahrenheit up to about 1,000 plus. And as you can see, this stands for endpoint, and this stands for volume percent recovered in a distillation. And what this 69.4 means is that that percent of the oil is recovered if you try to distill it, which means that the rest of it's left in the flask and doesn't distill over, i.e. the asphaltic portion of the resid. The autoclave activity test that we used is described on this slide. We pre-sulfided the catalyst in a quartz reactor separate from the autoclave, discharged it with mineral oil to keep the air from getting to it later. We then put 30 grams of this catalyst, pre-sulfided in an annular basket in a stirred autoclave and used 165 grams of resid. The system was pressured up to 1,000 psi-G with hydrogen and then heated to about 600 degrees Fahrenheit. And the pressure was then allowed to drop as the reaction occurred. Samples are taken every hour over a 5-hour period, and the results were evaluated with second-order kinetics. The catalysts that were tested in this particular phase of the work are shown on this slide with this nomenclature, but you can see that the percent of MOO3 varied quite a bit, 22, 18, and in between, cobalt oxide varied accordingly. The surface areas of the catalyst are shown here, and that'll be important in a minute when we discuss the graph after this. But the relative weight activity expressed in terms of percent of a commercial reference are given here. And what a relative weight activity is, for those who are not familiar with it, is the rate constant for the catalyst divided by the rate constant for the reference catalyst for the same test.
What's the reference catalyst here?
I'm sorry?
What did you use for a reference catalyst?
It was a catalyst called RF11.
Commercial.
It's a commercial catalyst. It's made by American Scientific Company. This graph shows these relative activities normalized with the surface area, plotted against the molybdenum concentration, normalized with the surface area, because different supports were used to make those samples that we saw on the previous slide. The supports didn't all have the same surface area. I was overjoyed the first time I ever saw this plot, because it indicated that our model was maybe valid. We could at least, draw a straight line through the data points we had. One interesting aspect here that we felt was important too is that we subjected all these samples to X-ray diffraction to see if we could find COMO04 in the finished catalyst. And if we did, it told us that if you can see the metals phase in the finished catalyst, the catalyst is probably going to be bad because the dispersion won't be as high as it needs to be. We didn't find any COMO04 in this sample. In the sample down here, which had the same MO03 loading, the normalized loading, we did find some, and that explains this difference in relative activity. So that was nice. After we did this, we decided to try to test this idea in another system, which consists of light diesel, a light diesel test, because diesel isn't nearly as heavy as resid. It doesn't have the diffusion, doesn't experience the diffusion resistances that in a catalyst like this that the resid does. And we felt we might get a cleaner set of results. Also, we had an opportunity to evaluate the catalyst by virtue of choosing light diesel in a flow reactor that a friend of mine was running at the time. But diesel, as you can see, we have the nitrogen level is shown here, which is not important for the present discussion, but there it is if it should be of interest to anybody. The sulfur is lower than it was in the resid, 0.65 weight percent. The boiling range, as you can see, is lower, 362 Fahrenheit to about 630. That is probably all the properties we need to look at on this slide to go on. The activity test, in this case, consisted first of pre-activating the catalyst to make the active sulfides on the surface. And that was done in the reactor. The reactor conditions that were used were 700 pounds, a space velocity of 5 reciprocal hours. That means 5 volumes of feed per volume of catalyst per hour. But the hydrogen rate in units that the oil industry uses was 3,000 standard cubic feet per barrel. And the temperatures that were used ranged between 675 and 725 degrees, so that my friend could get the kinetic data that he wanted. A plot of 4 catalysts that were evaluated this way is shown here, and I chose at that time to use the origin as one of the points. If I had to do it over today, I might choose to come up here a little bit, because usually the reactor walls or the support ends up having a little bit of activity. But as you can see, this did make a nice straight line, so it showed us one more time that we we seem to be on the right track, and that the percent MOO3, which is 10, 15, 20, certainly above 12% where the catalyst of the day had been. If the MOO3 were raised up to around 20%, then we still had seemingly the activity increasing with metals loading, so that looked good at that stage. This slide shows some finishing up work that we did for the patent department after the work we just discussed. So we could get some coverage on this work. And the slide's pretty busy, but what I want to show you is that one system we have here was one consisting of this loading in aluminum. To make these catalysts, what we actually did was to cobalt some ammonium heptamolybdate, some cobalt nitrate with precipitated alumina powder, bomite alumina, which is aluminum oxide monohydrate. And our objective was to calcine subsamples of each sample, measure surface area, and see what the X-ray people had to say about whether they found mixed metal oxides. And as you can see, they started finding them at about this temperature with this metals loading right here. And the surface area of the catalyst was about right here at that point. Now, if we lower the metals loading to these values, you can see that we don't start finding COMO04 until a much higher calcination temperature and a much lower surface area. In other words, it looked at this stage like indeed, as we were visualizing from our model, the amount of surface area that was required to distend the molybdenum trioxide and so on was proportionally lower with proportionally lower metals loadings. So it all seemed to still be fitting. Well, back about the second slide, I believe it was the third slide, I mentioned that we had a sort of an empirical theoretical result that the surface area was given by the percent MOO3 divided by 0.14, rearranged algebraically a little bit. Well, this experimental work gives the same answer when you take as a basis the point at which COMO04 starts to be detectable. So it was a beautiful model at that point, and it tied in nicely, and we were able to get some patent coverage on the basis of this, which of course is one of the necessities of industrial research all over the world. Well, at about this stage of the game, my friend Dr. Ryden Richardson saw the potential of this kind of idea in the denitrogenation end of hydrotreating. All the work I had done had been in desulphurization. And what Ryden did was to get some support, some finished support, and start impregnating it by soak techniques with a solution with an excessive solution containing molybdenum and nickel and phosphorus, and loading up the supports with what we call NiPMO levels that were higher than the standard 18% MOO3 and corresponding nickel oxide and phosphorus that we were used to at that time. He was able to get about, as I recall, 23, 24% molybdenum trioxide and also higher levels of nickel and phosphorus on the supports like that. And we tested those. But first, the properties of gas oil, which is in between diesel and resid, are shown on this slide preliminarily. You can see the boiling range starts low here, but it also goes up higher than it does for diesel, and not as high as it did for resid. The percent recovered was essentially 100%. Sulfur level of 1.35, and in this case, being a denitrogenation emphasized process, we pay close attention to the feed levels of basic nitrogen and total nitrogen. In industry, by the way, we certify or qualify our catalyst from the catalyst manufacturers on the basis of the total nitrogen. test itself consists of, again, pre-sulfiting the catalyst in situ. The reactor conditions in this case are 1,400 pounds, a space velocity of 2, hydrogen rate of 6,000 standard cubic feet per barrel, and temperature of 700 to 725 degrees. It varies with the particular gas oil you're using as a feed, and the idea, though, is to get about 96–98% conversion of the nitrogen in the test. That permits you to study fairly tough molecules, but also lets you have enough product left in enough nitrogen left in the product where your analytical people won't have a lot of trouble with the accuracy of the analysis. Well, Ryan started his work around 1980, as I recall, and within 2 years or so, the information that was generated from our own laboratory work and testing was turned over to the catalyst manufacturers in cooperative programs. And the catalyst manufacturers were able to improve the supports with their own technology that we didn't necessarily know about in such a way that they got catalysts that were actually more active than we got in the laboratory. And so they improved our catalyst by their own means, another 20% or so. Anyway, this slide shows you, taken off the map, a picture of progress for denitrogenation catalyst from the inception to the present time. This catalyst, which is arbitrarily given a 100 activity, was made back in the 50s, and it consisted of copelleting, cobalt and molybdenum and aluminum, and calcining that. This stage 2 catalyst consisted of changing from cobalt to nickel. This stage 3 consisted of using extrusion technology to make the particles rather than copelleting. This big improvement here came from introducing phosphorus. This improvement came from changing the particle shape from cylindrical to shaped, either trilobal or quadrilobal or something like that, and the overall particle size was made smaller. Hence the diffusion resistances were lowered. And this represents the present technology that was permitted by the high metals work. There exists now potential for having a catalyst with activity right about here, but we have to let maybe another year pass before we can see if we're really going to be that good. Well, this slide has already been discussed in various ways today. This is a review of the theories that were being considered after we started the work we were doing, and the intercalation theory and the synergistic contact model and the monolayer theory. The monolayer theory, I suppose, would be, for a while it was my favorite schematic representation of the COMOS layer, but I'm not sure it is anymore. Anyway, it's schematic. Now, something that I think is closer, maybe closer to the truth. After all that I've told you about was done, I finally somehow thought of the question that maybe I should have thought of a long time ago, which was, instead of considering just COMO2S4, what happens if you assume that the working catalyst really is MOS2, dispersed on an aluminum support? Well, you can go to the literature one more time and you can get the structural data for MOS2. And if you make a projection of that, it looks like this. That's a nice, pretty arrangement. You can imagine that it's highly dispersed. And I won't go into the stackings that were discussed this morning and so on and so forth. I don't know enough really to bridge the gap between this and that right now. But you can, at the stage we were at least, you could reasonably ask yourself, well, suppose we introduce a promoter atom. Where do you think they would go? Where would the cobalt go or the nickel? And I think most people would consider it reasonable that they would go in the places where the most space is left, which would be like maybe here and at the corners. And if you violate three-dimensional crystallography a little bit and just take that two-dimensional representation and draw those in, looks like that. Now I'm going to play trick on you, so hang loose for a minute, but I'm going to show you the slide that I showed first again now, and maybe flip-flop between them a couple of times to let you see that the density of packing of these atoms is about the same here as it is in the first slide. The bonding may not be quite the same. For example, well, it's hard to say. There could be some molybdenum bonding here, although in MOS2 it's not. In the bulk structure of MOS2, there's not considered to be any molybdenum bonding. But if you have something stabilized on support, I guess you can postulate some other things if it's stationary, and so on. But now, if you look at this one, I've turned it sideways so that you can sort of see what the molybdenum sulfur entities look like. And you can see that the cobalt atoms are arranged around these entities like so. And one more time back, and one more time forward. The idea here is that it may well be the case that the bonding, the molecular bonding in the projections, or more properly stated, the difference in the molecular bonding in these two projections may be enough to spell the difference between a very active catalyst and a not very active catalyst. But in terms of the simplistic models we were trying to use to take advantage of higher loadings to get higher activity, that wasn't a consideration. And the reason that the COMO2S4 model and the MOS2 model with postulated cobalt positions give about the same result in terms of projected loading is that the packing density of the atoms is about the same in the projection. It just happened to work out. Now, we heard from the Iowa State people this morning about Chevrolet phases, and one of the things that I found out when I delved into the literature a little bit more about this same time was that you can find a structure that of this material that's nearly cubic. It's rhombohedral, but it almost isn't. It's just nearly cubic. It's got this little octahedron of molybdenum atoms surrounded by the sulfurs, and as was indicated this morning, for the low transition metal version of some of these, you have these nickel, in this case nickel atoms that appear to be somewhat dislocated in these regions. And to me, at this time, this model was pretty appealing because I like the idea of the promoter atoms being able to whiz up and down these little channels between these entities like this, because it seemed to me that they might be able to have a better chance of chemisorbiting the reactants. Well, I don't know if it's right or not, but if it should turn out that this is a good representation of the active material in hydrotreating catalysts, by going through calculations like were illustrated at the first of my talk, you can estimate that about 40 or 50% MOO3 equivalent can be stored on support of similar surface area. And if one can figure out how to get Chevrolet phases dispersed properly on supports with 300 square meters per gram surface area, for example, we could up our activity some more, maybe by quite a bit. If it turns out that this model isn't correct, then we've maybe reached the limit of our improvement by way of extra metals loading and have to look elsewhere for other improvements in hydrotreating catalysts. Finally, I would like to acknowledge Ryan Richardson again for his contributions in the work, and also Jerry Kalinowski and Pauline Morgans and Rudy Gonzalez for technical assistance to Ryan and me both during the course of the project. Thank you very much.
The paper is now open for discussion.